Hello and welcome to NASA headquarters in Washington, D.C. I'm Steve Cole with the Office of Communications. We're here today to tell you about NASA's next Earth science mission, the Orbiting Carbon Observatory 2, set to launch on July 1st. OCO2 is NASA's first dedicated spacecraft to measuring carbon dioxide in Earth's atmosphere. This greenhouse gas is a key factor in understanding climate change. Today we have 4 panelists here to talk to you from the mission. Let me introduce you to them. First will be Betsy Edwards, OCO2 Program Executive from the Science Mission Directorate here at NASA headquarters. Ralph Basilio, OCO2 Project Manager at NASA's Jet Propulsion Laboratory in Pasadena, California. Mike Gunson, OCO2 Project Scientist, also from JPL. And our fourth presenter is Anne-Marie Eldering, OCO2 Deputy Project Scientist at JPL. After our presentations, we'll take questions from the media here in the auditorium, on the phone line, and from people who are watching on NASA television. If you're watching online and would like to ask a question during the question and answer period, you can post it to Twitter and use the hashtag AskNASA. Okay, then we'll begin with Betsy.
Good afternoon. The Orbiting Carbon Observatory 2, we call it OCO2, will join our 17 operational Earth science missions in studying the Earth as a system when it launches from the Vandenberg Air Force Base in California on July the 1st. If we could have our first picture, please. These missions, together with our ambitious set of Earth science, airborne and ground-based measurements, will monitor the Earth's vital signs. OCO2 in particular will measure global concentrations of carbon dioxide and watch the Earth breathe as we measure the greenhouse gas that drives climate change. The timing for this mission couldn't be more appropriate given the administration's Climate Action Plan recently released, focused on reducing carbon emissions. As Steve said, OCO2 is our first NASA mission dedicated to studying carbon dioxide. And this makes it of critical importance to the scientists who are trying to understand the impact of humans on our global climate change. If we could start the first video, please. This calendar year will be an auspicious year for Earth science, as it will see 5 mission launches. We are number 2. These launches will seek to address the most pressing issues facing our planet today. Issues like sea level change, freshwater resources, extreme weather events, and of course, climate change. Climate change is the challenge of our generation. And NASA is particularly ready to study things and to provide information on documenting and understanding what these changes are in the climate, in predicting the impacts of these changes to the Earth, and in sharing all of this information that we gather for the benefit of society. As we launch OCO2, the data we provide will help our decision makers at both the local and federal levels to be better equipped to understand carbon dioxide's role in climate change, because OCO2 will be measuring this greenhouse globally and understanding and providing new insight into where and how the carbon dioxide is moving into and out of the atmosphere. The OCO2 satellite has one instrument, a 3-channel grating spectrometer. But with that one instrument, we're going to collect hundreds of thousands of measurements each day, which will then provide a global description of carbon dioxide in the atmosphere, and it's going to be an unprecedented level of coverage and resolution, something we've not seen before with previous spacecraft. If we could see start our next video, please. The OCO2 spacecraft, because of the way it's orbiting in its polar orbit, will see locations on the Earth at the same time of day but every 16 days, and then over the change of seasons, providing new insight into how carbon dioxide levels are changing over time. And this change will ultimately provide patterns over weeks or months or years as scientists attempt to unravel the mysteries of the carbon cycle. The OCO2 spacecraft came into being as the result of the unfortunate 2009 failure of the launch vehicle that contained the original OCO spacecraft. But due to the importance of this mission to the scientific community and to society, NASA was given permission to rebuild the satellite. Shortly after the loss of our first satellite, the science team from the Japanese Greenhouse Gases Observing Satellite, or GOSAT, reached out to NASA and invited our OCO science team to participate with them in evaluating and understanding the GOSAT data. And this collaboration has now gone on for several years after the launch of GOSAT in 2009. And the science team here has now been using that GOSAT data for the past several years in helping to refine their data processing algorithms. Of course, this cooperation is benefiting both teams, and it will be strengthened as soon as we get OCO2 on orbit and can share our data with them. The scientists are eagerly anticipating the ability to merge our OCO2 data with their GOSAT data and helping them to advance their knowledge in understanding the carbon cycle. The OCO2 mission, in conjunction with our robust set of Earth science, space-based and airborne observations, our ground-based measurements, and our data processing activities, will yield unparalleled new insights into the Earth as a system. We are eagerly anticipating the July 1st launch of OCO2 so we can all watch the Earth breathe. And now I'd like to turn it over to our project manager, Ralph Basilio.
Thank you very much, Betsy. So NASA's Jet Propulsion Laboratory and Orbital Sciences Corporation have been working quite diligently since the OCO2 project's inception in March of 2010. Now, our project team has actually been working quite hard to deliver on the promises that were made on the original OCO mission. Basically, obtaining measurements of carbon dioxide from space with the precision, resolution, and coverage that's required in order for us to improve our understanding of the carbon cycle and the global climate change processes. Now, we've taken full advantage of all of the existing designs and documentation from the original OCO mission. Sometimes we refer to OCO2 as a carbon copy of the original OCO mission. Well, it's not quite an identical twin, but I am happy to report as the project manager, our team has done a great job. We fully expect to meet the technical, schedule, and cost commitments. Now, may I please roll the first clip? So, in the 8 months since August of 2013 to April of this year, the observatory, which consists of a standard spacecraft bus and a single instrument, went through a comprehensive and successful ground test program. The ground test program also included a simulation of the environments that the observatory is going to see during the launch and actually during space operations. So the dynamic environment of the launch vehicle, as well as the cold and hot temperature extremes and the vacuum of space. After the observatory was tested at the orbital facility in Gilbert, Arizona, it was transported overland to the Vandenberg Air Force Base on California's Central Coast. And upon arrival at the payload processing facility, the shipping container half was hoisted off of the observatory, and the protective black plastic covering the observatory was removed. And once that was completed, the process team there at Vandenberg was able to complete some additional activities. So upon arrival at that payload processing facility, we've done three important things. Number one, we've gone ahead and reconditioned and recharged our battery. Number two, we've gone ahead and performed what we call a series of post-shipment tests. We really want to make sure that the spacecraft meets our functional and performance specifications even after the overland transportation. And finally, we've added enough hydrazine fuel on the observatory to make sure that we can operate the mission well beyond the nominal 2-year lifetime. Now, combined operations, meaning operations between the launch vehicle and the observatory, commenced this last Tuesday, June 10th. And combined operations will continue through launch. So if we can roll the second clip. So the United Launch Alliance Delta II rocket will launch the OCO2 Observatory into space on July 1st at 2:56 a.m. Pacific Daylight Time. About 5 minutes into the flight, the booster or the first stage will burn out and be jettisoned. The launch vehicle's second stage will ignite, and shortly after, the two protective halves of the payload fairing will separate, exposing the observatory to the space environment. Now, after a relatively long, unpowered cruise phase, the observatory will actually be separated from the launch vehicle second stage. We hope to be able to capture this separation event through a camera that's mounted on the launch vehicle's second stage. The separation work will occur in broad daylight. Now, about 3 minutes after the separation, there'll be an onboard command sequence in the observatory that will begin executing. So 3 primary things will happen. Number 1, we'll establish communications with the ground. Number 2, this observatory will begin stabilizing itself. And finally, number 3, the solar rays will deploy. Now, we expect the observatory to be in what we call a power positive state about 2.5 minutes after launch, or 2 hours and 30 minutes after launch. And what does that mean? That means that the solar rays are going to provide well than enough power to go ahead and provide the resources that are required on the observatory. So after the spacecraft has been stabilized, we will basically go through what we call a spacecraft checkout phase. That'll take on the order of about a week or 2. And what does that mean? We will go ahead and configure spacecraft components for in-flight operations. For example, turning on the GPS or the Global Positioning Satellite System receiver. And upon completing that spacecraft checkout period, we'll go ahead and start what we call the ascent phase or maneuver phase. So if I can get the next graphic on the slide, please. So we'll perform a series of what's called propulsive maneuvers to raise the altitude of the observatory to the 705-kilometer orbiting altitude or operational altitude. And the spacecraft will take its place as the lead satellite in what we call the afternoon or the A-Train constellation. Now, the constellation is a group of satellites that will be flying in formation with one another. And they fly in formation because we want to get a comprehensive and complementary set of science data. Now, once in the A-Train operational altitude, we will check out the instrument, and that too will take about a week or 2 to complete. We really want to make sure that the instrument, again, performs and functions the way it did on the ground. So once that's completed, we'll go ahead and conduct normal operations, which will consist of basically transitioning between what we call nadir mode, where the instrument is pointed straight down towards the Earth, and what we call glint mode. So glint mode is where the instrument is pointed to the sun's glint spot on the globe. We want to make sure that we get acceptable measurements from the dark oceans. In addition to that, each day we'll be looking at what we call a ground validation target, maybe like the one at Lamont, Oklahoma, or maybe Park Falls, Wisconsin. We get that data because we'd like to be able to go ahead and make comparisons with the space-based measurements and make sure that they meet the requirements. Now, I'm an engineer, and an engineer is trained to solve problems. With the complete loss of the original OCO mission, it was heartbreak. The entire mission was lost. We didn't even have one problem to solve. Now, on behalf of the entire team that worked on the original OCO mission, we're excited about this opportunity to finally be able to complete some unfinished business. So without any further ado, I'd like to introduce you to Mike Gunson. Mike is our project scientist, and he'll explain to you why this mission is as urgent as it is important.
Thank you, Ralph. Yes, I'm going to talk briefly about some of the science motivations for this mission and why atmospheric observations from space of carbon dioxide provide new insight into the underlying carbon cycle processes which we'd like to understand better. To date, much of what we know comes from a few extremely important ground-based observations, one of which is quite famously the Keeling curve, a series of measurements started in 1957 by Charles Keeling from Mauna Loa. And to date, this kind of measurement made in a number of stations around the world has provided us the insight we have into what's happening in the carbon cycle. If you run the animation, what it shows is quite clearly that there's a steady increase in atmospheric carbon dioxide concentrations with time. Over this period of time, human beings have released hundreds of billions of tons of carbon into the atmosphere, so that even today, with the modernization of the developing world, we start to see that we're releasing something like 40 billion tons of carbon dioxide each year, and this is increasing. But at the same time, as Betsy remarked, we can see that this has this annual cycle of dropping every summer as the in this case, as the northern hemisphere, as the forests and plants start to grow. And this is the Earth breathing. And that's why we've used that to describe some of what we see here. But it's not just the planets, plants and forests. The oceans play an equal role as well in absorbing some of this carbon dioxide. And every year, what's quite remarkable is that over time, half of what we've released has been absorbed by either plants or the ocean, but it's very variable from year to year. Understanding what controls that variability is really crucial. If we can do that today, it might inform us about what might happen in the future. Will those processes continue, or will we see an abatement in their ability to absorb carbon dioxide? And does that increase the amount that resides in the atmosphere, obviously having climate change impacts, enforcing perhaps more change? So to do this, what we'd like to do is extend the measurements that have been made so carefully at the surface at places like Mauna Loa and do this globally. So we've planned very carefully with OCO2 to make these very careful, precise measurements in a truly global sense, to give us a better insight into the underlying regional behavior of the processes which control carbon exchange between the surface and the atmosphere. In doing this, we were very fortunate because this is, to say the least in my experience, a tricky measurement. We were very fortunate to have the collaboration with our colleagues in Japan and the GOSAT team. They provided us with a data stream which was a great example of what we think we will see and hope to see with OCO2. And we've developed both the processes for processing that data, but the validation techniques we will need. But in doing so, one thing that certainly was a surprise to me was that a couple of my colleagues also made what I think is a fantastic discovery. It's been known for some time that when plants absorb sunlight and undergo photosynthesis, a tiny amount of that energy is released as a fluorescence photon back to space. So we believe we'll have the opportunity to provide some new insight into what's happening at the surface in plants by looking at what we call solar-induced fluorescence. In this still, one of my colleagues went as far as to look at what we might expect to see with OCO2 over a month's period. As you can see, what is shown or highlighted in the brighter colors, the reds and oranges, are the great forests of the world, like in the Amazon, the Congo Basin, and in Southeast Asia and Indonesia. But you can also see other regions as well, which are probably important, in the eastern United States, there's an awful lot of forest and agriculture. And you can also see in Eurasia, the broad expanse of forests that are so critical to the carbon cycle there too. So with these, we hope to provide not only very precise, detailed measurements of carbon dioxide, but also potentially a new measurement which could inform carbon cycle science. And with this, I'm just excited to get my hands on some new data in the next couple of months. It's what we've been waiting for some time. And with that, I'd like to introduce Anne-Marie Aldring, the Deputy Project Scientist.
Thanks, Mike. So Mike talked a little bit about the big questions in the carbon cycle science and the measurements OCO2 will make. But how well does OCO2 need to measure carbon dioxide to answer that question? And how are we going to do it with our instrument? So the short answer to my first question is one part per million is our goal for the sensitivity of this measurement. And to give you an idea of how much that is, we made a little jar of black beans that represents the concentration of CO2 in the atmosphere, which if you saw on Mike's graph is something on the order of 400 parts per million. So if this was 400 parts per million carbon dioxide molecules and I want to know when it changes by 1, I've got to be able to tell when I add that many beans to the column. So it's a really sensitive measurement that we're aiming at. And Mike also mentioned the fluorescence. The fluorescence change to the radiance is maybe 1 or 2 beans that change. So we have a real challenge and an instrument that we think is up to it to make these precise measurements of carbon dioxide. Another way to help you see why we need this precision is this movie of a model field of carbon dioxide. So we're showing you a movie that was generated by our colleague Leslie Ott over at Goddard Space Flight Center of the total column of carbon dioxide, the amount between the surface and the ground, which is what OCO2 has sensitivity to. And you'll see the lighter blues or the deep blues are about 370 parts per million, lack of color is about 380, and 390 is shown in the deep reds. One thing you'll notice is if you just look from the northern reaches of the globe to the southern, there's just some small changes from a moderate blue to maybe a moderate red, something like 10 parts per million change from the north to the south. But if I was trying to understand the role of the forest in North America and Eurasia, you can see that the changes from those two regions are smaller, on the order of 1, 2, maybe 3 parts per million. So we really have to get at these details and these precise measurements of carbon dioxide to understand the transfer. The other features you see in this map are things like the low concentrations in the northern hemisphere because the active plants and trees are drawing in the carbon dioxide. And there's some areas that actually have fires and biomass burning going on that show up as red because of the sources of carbon dioxide. So we'll learn more about these sorts of features with our measurements from OCO2. So how are we going to do this? Well, the main principle of our measurement is shown in this still. We're a measurement that relies on sunlight reflected off of Earth's surface back into the instrument. So we look at reflected sunlight, and that light is changed a little bit by the molecules that we're looking through that absorb light. And specifically, we'll focus on the absorption changes because of the carbon dioxide. Another feature of this measurement is that we want to look at just a small area at a time. We actually only measure over 1 square mile with each measurement because if you're trying to make a measurement from a satellite, clouds can get in the way. And the smaller the area you measure, the more likely you are to see around those clouds or to be able to look in areas that are cloud-free. So that's the general principle of how we make the measurement. And in my last graphic, I'm just showing you a little more detail of how it operates. So the telescope here, the part that looks like an eye, is where the light goes into our instrument. And then we've just traced the light through as it goes from the telescope through some lenses and then hits what we call a grating. Now the grating has an important function because it's the part of the instrument that splits the light into 1,000 different colors. And you can look at the back of a CD, I don't know if I can shine it into your eyes, but it's the same concept that these grooves on the back of the CD disperse the light into many colors, and that's what the grating does for us. So once the light hits the grating and is dispersed into 1,000 colors, it goes to the detector where we actually collect the measurement. And the lower figure is just sort of showing you how this dispersed light might look over 1,000 colors. We actually look at this type of measurement in 3 different regions of light with the OCO2 instrument. One of those is focused on the area where clouds absorb, so we can see if it's cloud-free or not. And the other 2 are focused on regions where carbon dioxide specifically absorbs. So that's a little bit about how the instrument works and why we think we can achieve these precise measurements. So in summary, I think it's fair to say on behalf of the team, we're all very excited about our upcoming launch, 2:56 a.m., July 1st, Vandenberg Air Force Base out in California. And we're excited about the science we'll do. The OCO2 mission will collect, as Ralph said, the measurements with the accuracy, coverage, and resolution that we need to answer these important questions about where carbon dioxide is being absorbed and released in the natural global cycles across the globe. Thank you.
Okay, thank you to our presenters, and now we'll take some questions from the media and those watching online. Again, if you're watching online and would like to post a question, go to Twitter and use the hashtag AskNASA. First, we'll take questions here from the press in the auditorium. Please identify yourself and go ahead.
Hi, I'm Dan Vergano. I'm with National Geographic. I was wondering about the resolution you mentioned it's 1 square mile, that's the grid. Is that a good enough resolution that we'll be able to see the big stationary emitters that are of such concern in regulations now?
Yeah, I've got that to you. So the question is, will that 3 square kilometers be enough to resolve the big emitters? I've done back of the envelope calculations that show that some of the big emitters will certainly stand out if you get close to the plume or the center of emission. Work done by colleagues with the GOSAT data showed that large urban areas like Los Angeles and Mumbai, I believe it was in the examples they looked at, you can certainly see the buildup of carbon dioxide due to human activity in the cities compared to nearby regions where there's no human activity. So yes, in principle, we fully expect to be able to see points where there are large emissions compared to other points nearby. But this is really not a mapping mission, so it depends where our orbital track crosses. This is much more of a sampling mission than it is a true global mapping mission.
Okay, another question here.
Hi, Eric Hand with Science. I guess my question's for Betsy. OCO3, the flight spare, there were plans to take it up to the space station and have it complement OCO2 in observations, but it was left out of the president's budget. I know budgets are always uncertain, but you know, as far as I know right now, it's essentially sitting in a box. What are the plans to going forward with OCO3?
Well, indeed, our current activities with OCO3 are being put on hold, and we're using the rest of our fiscal 14 funds to get them into a stable state so that we can put them into storage. But it is still an important activity, and you know, we've talked about the importance of this particular measurement. Right now, the fiscal 15 budget has been, you know, we're looking at all of the priorities of the things that we have. Clearly our operational missions and some of our development activities do have a higher priority. We do expect that at some point, you know, we're getting good data from our atmospheric measurements. OCO2 is going to give us fabulous data. So we hope to get back to OCO3, but right now the budget doesn't allow for us to do that, but we're putting it into a position where we could go back to it at any time.
Okay, we have a number of questions on social media. Jason?
Indeed. Hi, this question comes from Twitter user Colin. What possible problems do you expect with this project that could potentially prevent accurate numbers and readings?
I'll take that one first, shall I? If the question is what could impede us from getting those accurate numbers, we've taken a lot of care to ensure that we understand how this whole system works so that we can reduce the likelihood that anything will impede us getting those accurate numbers that we need to actually inform carbon cycle science. There's always the unexpected, but you kind of have to roll with those when they occur. But we've planned this very, very carefully, and I'm personally not expecting well, you can't expect the unexpected, but there's nothing that we foresee impeding our progress on this. What do you think, Ralph?
Yeah, the only thing I would like to add is that, as I mentioned before, we subjected the observatory, both the spacecraft bus and the instrument, to a comprehensive ground test program. The instrument was fully calibrated. We went through a lot of different activities before that instrument left the Jet Propulsion Laboratory. We feel confident that this is going to work. We've done everything that we can on the ground.
Wonderful. This next question comes from Twitter user Jill Grace. Will the instrument be able to differentiate between natural versus human-generated carbon?
Just a hello to Jill. She's a middle school teacher in California, I suspect. It's very difficult from the just measuring carbon dioxide alone to distinguish between the two, between anthropogenic and natural changes to carbon dioxide. You have to resort to other means. Isotopic signatures are a very important method for distinguishing the contribution of anthropogenic sources. But in the overall use of this data, we do expect to be able to say something about the relative contribution of anthropogenic and natural contributions to changes in carbon dioxide.
Wonderful then. Another Twitter question here from Grace Bow. Will OCO2 be high enough to see the ozone layer?
Okay, so I'll take that question. So the OCO2 is in fact well above the ozone layer. We'll be flying at 705 kilometers, but we've specifically chosen the wavelengths that we're going to use so that they are not sensitive to ozone. So there's really no absorption signals, no fingerprint of ozone in the wavelengths we're going to use. We did that on purpose to not get confused.
Okay. We have a question on the phone lines. Let's go to Irene Klotz from Reuters.
Irene, your line is open.
Needed a program cost, spacecraft and the launcher, and also if you could include what the original OCO figures were. Thanks.
Didn't catch the first part of that.
Was the question what were the original costs and of OCO and the current cost of OCO2?
Okay.
I think.
I guess that one's mine. Okay. Okay, so get my cheat sheet. The original spacecraft was about $275 million. This one was about $465 million, so there is about a $200 million delta. A lot of that delta is based on the fact that we did change launch vehicle. We were originally slated on a much smaller, less expensive vehicle, and we've now changed what launch vehicle we're riding on. We also did have a slight delay in the development of OCO2. Actually, slight, it was about a year, just over a year's delay, as we made the shift, as we were doing the competition to understand what our new launch vehicle would look like. And the team had to sort of stand down, so there was a period of time when we were trying to keep people working hard, but there wasn't as much of the work available for them to do while we made that decision to move to the next vehicle. We did make some re-engineering changes. Parts obsolescence happens. Your computers move faster than, change over faster than anything these days. So we had to do a lot of some replacement of parts as we were building up OCO2 versus OCO1, and so some of those parts became more expensive. And of course, there's the ubiquitous inflation that also hit us a little bit. So to put all that together, it's about the delta.
Okay, we have another question on the phone lines. Jonathan Amos from the BBC.
Once again, if you do have a question, please press *1. Make sure you unmute your phone and record your name clearly when prompted. Jonathan, your line is now open.
What are the key mysteries that you want to go after with OCO to close the gap on what we know about where the sources are and precisely where the sinks are as well? What are the key missing ones?
So I'll take this first and then hand it back to Anne-Marie.
All right.
Over the past few years, there's been a number of research papers published which have talked about the role of rainforests and whether we've got the balance right there, whether their response has been muted by the impacts of drought. There is some papers recently suggesting that semi-arid regions, grasslands, play a bigger role. In the past, there's been speculation that North America is one of the homes of the biggest sinks, natural sinks of carbon dioxide, a greening in North America, a greening effect. But these are just some of the examples of some of the difficult questions that are hypotheses that are very difficult to test without new data such as those from OCO2. What do you think, Anne-Marie?
Yeah, and similarly, the southern oceans have been understood to date to be a big region of exchange of carbon based on limited sets of measurements. So if we can get these global measurements, I think we can much more firmly realize if this is the correct hypothesis or if there's other explanations. And again, the other important aspect of OCO2 is each year is a little bit different, so we want to start to understand what drives those differences.
Okay, we have another question here in the auditorium.
Hello, I'm Kate Winkle from the Scripps Howard Foundation Wire, and I know that this project is going to bring a lot of new data and new information that scientists can use, but I know that you all are also concerned about what business people and what politicians do with this new information and new knowledge. So what specifically do you hope they take from what you learn in this program?
You, Mike.
Thank you, Anne-Marie. So, really, the bigger questions here are fundamentally driven by science questions. The processes or the what we understand about human activities is primarily driven by what we call accounting or inventory processes. We can actually count how many barrels of oil, tons of coal, etc., that we consume. It's really the fate of carbon dioxide once it's in the atmosphere that we're trying to really put our finger on. And if we can understand what's happening today, I think it's quite remarkable that over the past decades, we've seen that half the carbon dioxide we put in the atmosphere has been removed by natural processes, but we still aren't quite sure what the details are of which of those, which are the key processes involved here. So trying to get to a point of understanding the details of those processes will give us some insight into about the future and what's likely to happen over the next decades, even if we continue to consume more and more fossil fuels and emit more and more carbon dioxide into the atmosphere.
I think we would also be hoping that policymakers might use some of this information to, for example, start to take a look at the impact of some of the emission reduction activities that go on, or deforestation, and understanding what's happening globally.
Okay, we have some more questions on social media.
Wonderful. This comes from Twitter user Naresh asking, what is the life of this mission and how long will it take to survey the Earth?
Let me take that.
Go ahead. You can.
Well, this mission is set for 2 years, nominal mission. As I mentioned before, we have more than enough fuel on board the observatory to last for this 2 years. We're going to be doing what we call a 16-day repeat cycle, meaning that we're going to be looking at the same spot on the globe effectively every couple of weeks. We'd like to be able to look at data, look at the seasonal variations as well as the annual variations on the globe.
Wonderful. This question comes from Twitter user Robert asking, what do you hope to gain via future collaboration with other CO2 missions such as GOSAT-2 and potentially CarbonSat?
So let me take a shot at that one. So the end use of our data in terms of the science is by people who have models of the global atmosphere, the movement of carbon dioxide, the exchange of carbon dioxide, and they basically compare our measurements with their models. And the more data they have in general, the more precise they are, the less uncertainty they'll have on the answers that they get. So we've already had discussions of how people would do this analysis with our data and the GOSAT data together. And it's even been started, some folks have started working also using data sets like the AIRS, another NASA mission, and test data. So the more data that they use in this analysis, they're still going to get improved answers. At some point, you can have enough data, it doesn't matter, but we're not near that point yet. So we believe the answers about the exchange of carbon, the sources and sinks, will be better the more data we use in this analysis, ours and everybody else's together.
So there's one little other benefit of the collaborations. So as Anne-Marie was saying, this is very much a data-limited problem in understanding what's happening at the surface. And extending the record is important, but to repeat, this is a very tricky measurement, and we can learn an awful lot from each other in understanding what it means to actually provide a measurement that's at 0.25%, 1 part in 400. There's a lot of lessons learned from the GOSAT experience that we've shared in the international community, and there's a lot more to be learned with OCO2 and then with our international partners. It's not a problem simply solved in California, let me say.
Okay, thank you. Another question from the audience here, Dan?
Dan Vergano at National Geographic again. I just wonder if you could speak a little to make sure I understand. Are there limitations in this sort of looking down through the atmospheric column approach? I mean, is all the action happening at the surface that you're seeing, or are you going to be able to say something about what's going on at different levels in the atmosphere?
Well, it's a very good question. Carbon dioxide, once it's in the atmosphere, is very, very stable. There are very few loss processes, if any, until it reaches very high altitudes in the atmosphere. All the action, as it were, is the collision of a carbon dioxide model with the surface. So it's either absorbed by a plant and taken up in photosynthesis, or it's absorbed by the ocean and dissolved into the water. So the real challenge of making a measurement is to get that information nearest the surface. When you look at the Keeling curve or any measurement taken in the middle of Los Angeles, you can see the influence of all those surface processes, whether it's emission or it's absorption of the carbon dioxide. We need to do that globally, so that's why we've developed a satellite approach which particularly probes the atmosphere nearest the surface by using reflected sunlight. So that's where most of the air is, so that's where most of the information in the observation we're making comes from. It is influenced by what's happening up above, but that's more about atmospheric transport processes and which way the wind's blowing. What we really want to know is what's happening in the exchange at the surface. So fortunately, there's less air above the surface, and that signal is much smaller and the influence is smaller there.
Okay, thank you. Let's see, do we have some additional questions from social media?
Indeed. This question comes from Twitter user Patrick Butler. How long will it be before you have good data to work with for plant and water absorption as opposed to release in the atmosphere?
Could you say that again?
Sure. This comes from Twitter user Patrick Butler asking, how long will it be before you will have good data to work with for plant and water absorption as opposed to release in the atmosphere?
So, if I understand, a really good question. Some of these, our measurement approaches, Ralph mentioned, is to take what we call a repeat cycle every 16 days. So we'll come back to the same point on the Earth every 16 days or 2 or 3 weeks. That really kind of gives you an idea of the kind of information content that we can recover from these observations. It's temporally resolved at roughly 2 or 3 weeks to a month. So, but you have to account for seasonal variations and changes over the year. So you have to really have good data that extends over several months before you can really inform yourself about what's happening at the surface. So both from an emission point of view or from an absorption of the carbon dioxide at the surface, it's going to take us quite a few months of good data before you can actually speak to what's happened at the surface itself.
But I just want to throw in one other comment on that topic. Even to date, folks have published some interesting results where they use the carbon dioxide information, the solar-induced fluorescence that Mike has mentioned, and then other measures of water availability. And the science community is already learning how to combine those 3 variables to understand the plant-related processes and how that interacts with carbon dioxide. So I think there's already been pioneering work, and our data set can probably be used in continued analysis on that theme.
Wonderful. This next question comes from Twitter user Didi here, asking, are federal agencies or NGOs engaged with the science team to use the CO2 data set for verifying carbon source reporting?
So we had our first workshop earlier this year nearby in Maryland, which started to engage those kinds of folks in what particular use this kind of observation and measurement could be. We're still very much at the exploratory stage at the moment, and I think a lot of further progress hinges on when we can make good data available and see what those folks can make of it.
Okay, one more question from social media. Please.
Wonderful. This comes from Twitter user Daniel here asking, do we know the ratio per year of the amount of CO2 being added and the amount being removed to give us that ratio?
Very good question. Of the roughly 40 billion tons of carbon dioxide that's put in the atmosphere, roughly half is taken out. That's one of the more robust numbers over the past number of decades. So it's a 2-to-1 kind of ratio at the moment. But whether that's sustained in the future is one of the things we hope to start being able to probe and address.
And there's actually a science community that every year publishes an update on the global carbon budget, and they actually provide a year-by-year estimate. So we have the 50% on average, and folks have looked into what it is in particular each year.
Or the best estimates.
The best estimates, although the why is still not answered, so we have work to do.
Okay, and I think we have one additional question on the phone bridge, if that's ready to go ahead. Maybe we lost that question. Okay. Well, I think that ends the questions for today, and thank you for watching. Please stay online for more information about OCO2 leading up to launch, as has been said, July 1st. We have a website where you can get a lot more information. It's www.nasa.gov/OCO2. And OCO2 is the second of 5 Earth science launches this year. It's a very busy year for NASA. We also have quite a few exciting airborne and field campaigns coming up as well. There's a website where you can keep up with all that activity, and that is www.nasa.gov/Earth right now. And of course, you can follow along on all the different NASA social media channels as well to keep up with all these missions. It's an exciting year for Earth science. Again, thank you for watching. Have a good day.